I can.
I feel like you can, if there's, you can probably start as you can without the slides, and we'll get them to you as soon as they are ready. So
All right.
Our first talk will be by Iris van Zelst, talking about constraining the interior structure of Venus through coupled interior atmosphere models of CO2 and H2O.
Thank you. And it works now. Perfect.
Great.
So I will be presenting some preliminary results on this topic. It's not exactly as far as what I would have liked it to be, but at the end I have some questions for you. So let's see how that goes. So on the next slide, just to kind of introduce the topic, there is this feedback loop between the interior and the atmosphere. So if you see on the next slide, there will be this loop. And the first ingredient is the convection regime. This can be different things. It can be a mobile lid or some form of plate tectonics as we know it on Earth, or something different, stagnant lid, or nowadays people like the plutonic squishy lid with some delamination tectonics, anything really. But this convection regime to a large extent determines how much volcanism you have, and therefore on the next slide how much interior outgassing you have, and hence which gases on the next slide will make up the atmospheric composition. And this atmospheric composition determines to a large extent on the next slide the surface temperature. And this surface temperature is then, of course, a boundary condition for your convection regime and how the interior of the planet works. So then on the next slide, you have this closed loop of interior atmosphere feedback. And I'm interested in this, and I'm applying it to Venus, which makes sense for this conference. So on the next slide, I'm just going to quickly walk you through what I've been doing. So on the next one, there's a lot of builds in here, I'm sorry. We use the geodynamic code Gaia, which is kind of like the DLR in-house code, which does the thermal evolution of, in this case, Venus. And on the next slide, what I've added to that is that it calculates the abundance of carbon dioxide and water that is present in the melt. And then on the next slide, I'm calculating also how much of that carbon dioxide and water in the melt is actually outgassed, because sometimes the atmosphere is already saturated with a specific species and it doesn't want to outgas anymore after the melt. In order to kind of show you what I mean by that, I implemented the saturation curves, which you can see on the next slide. They are from Volatile Calc 2.0 by Newman and Lowenstern, 2002. This is an example for water, with on the x-axis the pressure that is relevant for Venus, and then you can see at which concentration in the atmosphere it's saturated with water and it wouldn't outgas anymore. And the same happens for carbon dioxide in the next slide. So that is kind of how we deal with limiting the amount that gets outgassed into the atmosphere. So on the next slide, then the last ingredient that we have on the next slide again is that we calculate from this the surface temperature. And the way we do that is by some equations, which I briefly highlight on the next slide. So we have the surface temperature Ts, which depends on a few things, which you can see listed there. And they again depend on a few things, namely the albedo A, the solar flux S, and the partial pressures of water and carbon dioxide, which is the Pi in the third equation. So to get some kind of feeling of how these parameters influence the surface temperature, I just plotted it up just to get some kind of intuition. So the partial pressure of carbon dioxide affects the surface pressure like this, very intuitive. More carbon dioxide, you get a higher surface temperature. The same is true for water in the next slide, although it has a slightly lesser effect. And on the next slide, we have the solar flux, which may have changed a bit during the 4.5 billion years of evolution of Venus. But in our model, as we can see in these equations, it doesn't really affect the surface temperature a lot. So the solar flux is an example of just an input parameter that we choose and doesn't change throughout our model. In the next slide, we also have a look at the albedo. And we see that, the higher the albedo, the lower the surface temperature. And this is again an input in our model that doesn't change throughout. So on the next slide, we are finally ready for some preliminary results. And these are very preliminary. So I'll walk you through them and I'll point out what's wrong. And then in the end, I'll solicit feedback. So this is a model where I have an initial mantle concentration of water of 50 parts per million. And on the x-axis, you can see the time evolution. So from 0, that's where we start the model, until 4.5 billion years. And then on the y-axis, we have the surface temperature. And the dotted line is the present day surface temperature of Venus. So what you can see is in the beginning, our starting surface temperature is 250 Kelvin. And in the beginning, in the first few 10 million years, there's a very steep increase of surface temperature, and then it kind of increases gradually. Interesting. It doesn't reach the current surface temperature of Venus yet, but yeah. So in the next slide, we can see kind of why this is happening, because now we're plotting the surface pressure through the model. And in dark blue, you can see the total surface pressure. And then in green, you have the partial pressure of water, and in red, the partial pressure of carbon dioxide. And as you can see, this steep rise in surface temperature at the beginning, in the first 10 million years or so, is because you have massive amounts of water outgassing. So we get a very large partial pressure of water. And then due to the saturation curves, like the atmosphere becomes saturated with water, there's no water outgassed anymore. So that stays constant, but slowly carbon dioxide starts to increase, leading to a higher surface pressure. However, as you can see on the y-axis, we're not close at all towards the actual surface pressures and building up the actual atmosphere of Venus of 90 bars. On the next slide, just to show you slightly differently the masses that we're considering. So we have a lot of water in the beginning, then it stays constant. And gradually we have CO2 increasing with time. But again, we're very far away from reaching the masses of the actual Venus atmosphere at present. So let's summarize this kind of preliminary result here in the next slide. We see that, well, the good thing is there is less outgassing when we apply the saturation curve. So, the code kind of does what we want it to do. Benchmarked it a lot, so it kind of works. However, on the next slide, one of the elephants in the room is that, of course, in our models, a lot of water is outgassed in the first few million years. And basically throughout the entire evolution, we see that according to our models, which is clearly incorrect, there is a steam atmosphere. And if we take reasonable values or, values for the mantle concentration of water in the beginning, we get way too high surface temperatures. So there is something going wrong there. And then next, another thing that we are kind of worried about is that there is very little carbon dioxide outgassed. So we are very far away from, the actual atmosphere we see on Venus. So this is all food for thought, and we'll put a pin in that for now. But I briefly want to tell you the outlook in the next slide of what I anticipate doing. Number one on the next slide is figure out what is going on and why this is the case. But then secondly, the way we want to apply this is by looking at the effect of the interior structure, like what happens if how do you change the mantle convection regime if you have a very differently sized core, for example, and how does that then affect this feedback loop between interior and atmosphere. And then next, at the moment, we are applying it to carbon dioxide and water, but we very much plan to apply it to the entire COH system in the next slide. So you get all these different species together. And then ideally, we also apply it to the CHONS system in the next slide, and you get all these as well. So that is the plan. But now, let's have a look at some questions for you in the next slide, because we can turn this around, this conference thing, and ask you questions. So what we see in our models is we get an H2O dominated atmosphere. And the question is why? We've tried a lot. We've looked at the literature. I mean, everything we've done in this code is taken different parts from different studies. So we are unclear as to why this is the case, and any insights would be highly appreciated. I know there's some people in the room who probably know this much better than I do, so any insights are appreciated. The next thing is that we have very limited carbon dioxide outgassing, which again raises the question, why is this? Because at this rate, it's going to take a very long time to get to the 90 bars that we see on Venus at the moment. The next, we were looking into the literature, and we saw that some people actually have an initial atmosphere on Venus of about 80 bars, 90 bars of carbon dioxide, and then their model evolution of 4.5 years add this CO2 to it, and then you get to what you see at the moment. So the question then would be to you, the community, should we add an initial 80 bar CO2 atmosphere? But then also, why would there be an initial CO2 atmosphere? Because you could probably argue that it is the result of outgassing of the magma ocean, but I was always under the impression that it would result in a steam atmosphere. So then maybe you want to start with a steam atmosphere? I don't know. These are questions. And then the last question I think I have for you is just in general, based on this, if you have any suggestions to build this secondary carbon dioxide atmosphere from scratch in these types of models, or if this is not something that works with these types of models. So with that, I leave you, and I hope to discuss at some point later. Thank you very much.